looked it up, but I should write it down on the board here just to be official. Final exam time. If I remember it right. I'm gonna guess, I think it's 27.
25th.
Right there. Anybody else will do it? So our final exam is Thursday of exam week at 12:30. So come here and I'll try to think of some kind of questions to put on the final exam.
Start. Like we didn't start.
Let me say a few words about the homework problem that I'm just passing back. So it was 2610 here, which refers to this data on page 275. So we have 3 states, we have 3 cities in each state, and then in each city there's 5 households and we're measuring something. So this is the data that we have. So there were some questions to deal with about this problem, this data set. And here's just a list of the data, which you don't need to see. But when I use the GLM, A, B nested in A, just straight off, I got this ANOVA table, and this would be the 2 F tests for questions in 2610. So the F statistics are 32 something and then 0.26. In both cases, the denominator is the mean square error, the 108 something. And that's indicated down here in caps output as well. Then in a later question, it says, well, in the first one, B is supposed to be a fix. And in a later question, it says, suppose B is random, do some testing. So when I gave this command, the subcommand random B there, I got this ANOVA table. And the F statistics are 124 or something and 0.26. So again, well, you can look at the expected mean square layout here and see that for testing A, the denominator should be B nested in A. And for testing B nested in A, the denominator should just be the regular error, as it's called 3 here. So those were the choices that were made in this ANOVA table up here. And so the F statistics are so extreme the decision to accept or reject this in both cases. Then in problem 2611, it asked us to do some confidence intervals. So the first one was for just the mean U11. And so I have to figure out the variance for that estimate. It's an average of 5 numbers, so it's 1/5 sigma squared. Sigma squared is going to be estimated by mean square error. And so put that in there and work out the variance of the estimate. And I pulled a number out of the t-table, and with 36 degrees of freedom, that's not directly in the paper t-table. So bracketing it, I saw those two numbers, and I said, well, let's just pick somewhere between 2.03, close enough. And then there's the square root of the variance there. So working that out, I get plus or minus 9 for the confidence. Then we want the 3 confidence intervals for the means on A, and each of these means is going to be an average of 15 numbers, and so the variance for one of them is 1/15 sigma squared. Estimate that with mean square error, put the number in, take the square root, and I get a variance on that. The number from the t-table, we're supposed to use 99% for these confidence intervals. So again, I had the trouble looking up 36 degrees of freedom. It wasn't in there, but I picked the number in the range there, 2.72. So that times the square root variance is a plus or minus 7. And then finally, it asks for some Tukey simultaneous pairwise comparisons between the 3 means. So the variance is going to be the variance of the difference, 1/15 plus 1/15 sigma squared. Estimate that with mean square error again. And work that all out with the square root of that. Tukey number from the Tukey table is not there directly with 36 degrees of freedom again, so I had to kind of bracket what I wanted, and I picked, here it is, you see 3.01 as my choice, dividing that by the square root of 2, which is easy to forget with Tukey's method, and times the variance, 3.796 over here, I get plus or minus 8.08. So the 3 confidence intervals would be the difference plus or minus 8.08. So those are the intervals that is asking us for in problem 2611. Okay. And I guess that's all then with this data that we have to worry about. So I'll put this aside. The handout, the one called 2 random factors and mixed models, which is where mixed models first came up. So somewhere in the middle of this, there's a heading for mixed models. There it is. A mixed model, 2 factors, There are the terms in the model, and then here's the statements about assumptions. And notice there are two possible models. One called the unrestricted model, where the interactions are just assumed independent normals. And then there's the restricted model, where the interaction of random variables are normal, but they satisfy various kinds of constraints. So we say there's restrictions on the beta parameters. So we talk about an unrestricted model and a restricted model. Now the thing that I want to point out here is something that I'm sure I didn't emphasize at all when we did this in class. There's a table of the various F statistics that are possible here with their expected mean squares. Before that table, notice this heading. Notice this heading. This table only applies for the restricted model. It doesn't apply for the unrestricted model. There would be a different table for the unrestricted model. And I think that's my fault because I should have that second table here for you to see as well, so you can see the two cases laid out in front of you. But anyway, this table, as it says, applies for the restricted model. So this is where Pedro says the F statistic for testing B has mean square error in the denominator. That's true for this model, but it's not true for the other model. So there's the dilemma that we're running into. What's the proper F statistic for testing B depends upon which of those two models we're assuming. So that's what we had in our class handout about that issue. Not clearly laid out, I would agree. But to check this out a little further, I prepared this handout that I gave you today. I took the data which was from problem 2 of the last test, which had 2 columns and 4 rows, 2 observations per cell. So this was the data. The specific numbers are in the actual test paper, but that's not of high interest. So what I want to do first is to take that data and do the regular ANOVA A-B interaction A-B. There's no nesting here going on. It's just a straight 2-factor problem. Random B, restricted model. So this is going to use the restricted model in the output. So here's the ANOVA table, the F statistics, and what else? Well, here's the expected mean squares that we'll use to figure out the denominators. And so the denominators of the F statistics are right here in the mean tab output. 3, the interaction is the denominator for testing A. But then for testing B or AB, we use 4, the error. So that's what it's telling us to do based on these expected mean squares. Now this is for the restricted model, right? There it is right there in the mean tab command again. So then I took the same data and I said, let's run it again, and let's take that restrict out. So that's equivalent to using the unrestricted model. So there's the minitab command, A times B, random B again, and leave off the subcommand about the restricted model. So this is the unrestricted model. And we get this kind of result here. Now, if you look at the F statistics for A are the same, for B differ by quite a bit actually, and for AB they're again the same. So something is changing in the F statistic for B, and we can see what's happening if we look down here at the expected mean square column. hit that light switch for you there? Daydreaming here. That's a little more visible, I guess. So if you look at this model and the expected mean squares, the proper denominator for AB would be 4, the error. The proper denominator for the next one, B, would again be 4. No, this isn't that piece over there. It would be the AB interaction. And then for A, it would be in the AB interaction. So we can trace down what would be the right F statistics by looking at these expected mean squares. And then the program already told us what it did. 3, 3, 4. And the denominator is choose. Now, so this handout has 2 messages. One message is you get different results depending upon which model you assume, right? In this case, the decision about accepting or rejecting H0 turns out to be the same here or up there, but it's not always going to happen. You could even have very different conclusions depending on which model you assume. So what is the statistician, what's the analyst supposed to do? I think we're kind of stuck basically because there's no magic word from on high that says which model should we assume. This is just a sort of a free choice of the analyst, of the researcher, and nobody says quite what one should do. So I don't have any recommendation to give you either. I should have said back earlier when we first encountered this issue, I should have said something like, always use the unrestricted model or something like that, just so you knew what I was looking for. I didn't do that, so I was kind of accepting various things that you might do. But out there in the real world, this is still a difficult thing. When you're reading somebody else's work, they've analyzed some mixed model kind of data. What did they assume? Most likely, they don't even tell you. They just present the results. They don't even present this kind of stuff. They just present the statistics and the conclusions, and that's all you see. Well, that's not a good situation. They need to be honest and say, what are they assuming for the model? But I don't see that done often enough. So what can we do? So the first message was, again, we get different results depending on whether we assume the restricted or the unrestricted model. The next thing that you could notice in this small example is that the formulas are easier in this case than in this case. They're shorter. So I say easier. Formulas are easier here in the restricted model than they are here in the unrestricted model. This has got extra terms in it that don't appear up there. Now I think this is one of the reasons why those crazy restrictions, seemingly crazy restrictions, ever got put out and studied. Because people noticed that the formula is simplified if you made those restrictions. And this is evident here by this formula, especially on B, being simpler than what we're seeing for B down here. The model is easiest to state with no restrictions. You just say the beta terms are normally distributed and that's it. So it's easy to state the model in this case. But then the results turn out to be a little more complicated than maybe we would like. So people have introduced those restrictions, giving us these kind of expected mean squares and simpler F statistics. wish I had talked about this kind of idea earlier in the semester when we first encountered the mixed models. But anyway, at the end here, I hope this tidies that weakness up a little bit by talking about these two situations here. Well, that's all I have to say today. So let me stop talking there and we can call off class. I've already told you that we're not meeting on Thursday. So use the time to study whatever you're studying for final exams. Okay. Okay.
So, Dr. Sievers,
Yes.
any tips on the exam, final exam? Any tips?
Any
Any
tips?
tips about the exam? Well, for the final exam, I'll probably emphasize the latter material instead of the earlier material. But I think the questions will be probably similar to the questions you'll see in that earlier test. So some numbers, some output to add some, make some conclusions, and there might be, I don't promise, there might be something related to some derivation.
It'll be a split plot and it will be chi-squared. The same.
Yes. So, other than that, I haven't thought about the questions for the final, running that test.
Will your questions on the EGE be similar to the exam questions?
Questions on the EGE will be similar to my exam.
Nothing out of the ordinary.
Nothing out of the ordinary.
Can we get some reviews for the DG?
Pardon?
Some review questions for the DG?
We don't have any.
What about the
I
previous
mean, the
exams?
previous DGEs relating to 664 were written by Dr. Stoley. It doesn't help you to review those questions because he's not making those questions this year. So, sorry, we don't have any. So the best thing to think about is the test that we had this semester as examples of possible questions for the final and for the DGE both. I took 2 points out because you got too many questions. I keep telling you guys over and over